In this lesson, we're going to take a look at the TCP/IP suite of protocols. At layer 4 of the OSI model, we find two of our primary protocols used on all corporate networks and across the internet as well. And they are the Transmission Control Protocol, TCP, and the User Datagram Protocol, UDP. Now, these two protocols are competing protocols. A segment will only use either TCP or UDP. And really, it's a matter of how certain is it that we have to get this information to the destination. If it's really important that you get this packet, this segment, this payload of data to the recipient, then you'll pay a higher price and use a more certain delivery mechanism, and that would be TCP. If we're doing that recipient kind of a favor and it really doesn't hurt us much if he doesn't get this information, then we might use a cheaper and faster protocol called UDP because it is fast and cheap and has very little overhead. Now, typically it's the application developer who wrote the application that created the data. He's the guy who knows what this data is and how important it is that we get 100% of this data over to the destination anytime we need to use the network relative to this application. So the guy who wrote the program makes a determination whether at layer 4 of the OSI model, the transport layer, we will initiate the TCP protocol, high cost, slower, but guaranteed delivery, because TCP is connection oriented. Before the sender starts sending any TCP segments, the sender will reach out to the destination and establish a session, a connection, by using a three-way handshake. The three-way handshake is 3 frames from source to destination, is sent a SYN or synchronized frame. The destination sends back a synchronized acknowledged frame, and then the source sends to the destination an acknowledged frame. This three-way handshake, these 3 frames establish the connection or the TCP session between sender and recipient. So that's the connection-oriented part, and that is 100% overhead. There's no actual data that commuted the network during that transmission. Now, the guaranteed delivery comes by the positive acknowledgement that the recipient must send for every segment he receives. So when the recipient understands they've established a TCP session with the sender, every segment that arrives, the recipient will process it up the stack to layer 4, verify that the payload looks like it's intact, and then at that point send an acknowledgement frame back to the sender for this segment that was just received successfully. This way the sender knows that it got delivered. Now, if a segment goes without an acknowledgement being returned to the sender assumes that the segment got lost and will simply retransmit that segment back to the recipient. So this is the guaranteed delivery of TCP. Now, UDP, as we said, is quite different from TCP. It has no overhead or very low overhead because there is no connection, no session established. There's no three-way handshake. So there's none of that overhead associated with UDP. When the UDP segment is ready for transmission, the sender simply sends it out. And that's the end of the story because there also is no acknowledgement expected or required from the recipient. So the sender simply puts the data on the network media and then assumes that it got delivered and doesn't actually know or care whether it really got delivered. So it is considered to be connectionless because there's no session established. It is also considered to be best effort delivery because there is no acknowledgement required for any of these segments that are delivered with UDP. Now, another thing that happens here at layer 4 of the OSI model, the transport layer, is the identification of the source and destination port numbers. These port numbers range from 0 to 65,535. There's a series of these that are referred to as server-side ports, also called well-known ports. And then there's a series of these port numbers that are referred to as client-side ports that come out of what we call the ephemeral port range. Now, ephemeral implies that these are temporary use. So here's how this works. A server on the network has a listener an application that is listening for inbound requests for the particular service. That listener is bound to a port number, so that when a request comes in to a specific port number, the server understands what service is being requested. The server hands that request up to the appropriate server-side application. If you look down at the bottom of this screen, you'll see a collection of the server-side port numbers that come out of the well-known ports. These well-known ports range from 0 to 1023 and are typically bound to server-side applications, services that run on your network that a client may request. So if a client is opening his browser and he wants to browse a web page, he'll send the request to server-side port 80. That would be the destination port 80. And that way, when the segment is received by the server, it looks at the port number at layer 4 header and says, oh, hand this request up to the web server. Now, the client must also receive that information back and hand it to the proper application running on the client computer. So the client also picks up port number out of this ephemeral port range, also called the client-side ports, ranging from 49,152 through 65,535. He simply makes up a number out of that range, let's say 58,000, and uses that as his source port number when he sends out his request. Now when the web server sends a response back, he sends it to destination port 58,000, and the client now knows to link this payload to the browser, and he hands that data back up to the browser so that the web browser can properly process this data. So here we have in the layer 4 header, TCP and UDP, we have source and destination port numbers that are also identified in this layer 4 header. Now here is a list of protocols, network services if you will, and their associated port numbers. As you can see, most of these port numbers range in that server-side port number range from 0 to 1023. However, we kind of overran our expectations on the number of server-side services that might eventually be needed on a network. So you see some of these server-side port numbers went outside of that well-known port number range, 0 to 1023. With this, we're going to take a break and we'll pick up with our TCP/IP suite of protocols in the very next lesson. In this lesson, we're going to be looking at several others of the TCP/IP protocol suite. Let's start with the Internet Protocol version 4. This is the layer 3 network layer protocol used by almost every corporate network and used by the Internet. So this is one of our primary core protocols used on all of our networks. Now the IPv4 address is a 32-bit binary address. In other words, it uses a string of 32 ones and zeros to identify a typically an unambiguous destination. In other words, when you want to send a file to a file server, you want it to go to a very specific file server, so this address must be unique and unambiguous to identify that file server uniquely. So we have a 32-bit binary string, and we see that about the second line down here on the slide. But off to the left of that, what we see is the dotted decimal notation for that same IP address. So the binary is to the right, the dotted decimal, something us humans can understand, something that might look more to us like an IP address, is off to the left. Below that, what we see is what we call the subnet mask. Now, if you'll notice, in binary, the subnet mask is a string of ones followed by a string of zeros. And in this case, this subnet mask is what we call a /24 mask insider notation. That's classless interdomain routing notation. And what that /24 designates is that the first 24 binary bits in this subnet mask are ones. And if the mask has to be 32 bits, that says that there are 8 remaining binary bits that have to be 0. Because we only have those two choices. It's either turned on as a 1 or it's turned off as a 0. Now what this mask identifies to the routing system, that also is a layer 3 network function, is which part of this address, 192.168.10.83, represents the network that the computer node, in this case a destination node, might be on. And the portion that is masked by zeros identifies which host or node on that network the destination is. So it's kind of like a boulevard and the house number. The boulevard is the subnet ID, and the house number is the host ID. The boulevard is identified by that string of ones in the subnet mask, and the house number is identified by the string of zeros in that subnet mask. An IP address is incomplete without both the IP address and its subnet mask. We don't understand anything about that node without knowing its subnet mask. So anytime you identify a node, you statically assign an IP address to a node, you must provide at least these two pieces of information. Now, typically, when you're configuring a node on an IP network, you will also need two other pieces to actually make it functional. Those first two, IP address and subnet mask, are essential, and the node simply will not operate without those two pieces. If you give it those two pieces, it'll operate on the network, but only on its local subnet. If you really want to operate on the internet or a larger corporate network, then you'll also need a default gateway, which is the IP address of the router that this node will attach to. So your default gateway is a router's IP address that is your path to all other networks, and that's your default gateway. And then the next thing almost all IP clients are going to require is a IP address for a DNS server. And because it's so important to have this DNS service available, very often you will identify not one but two DNS servers. One is the primary, the preferred, and then the second one is an alternate, just in case that preferred server is unavailable. So what is DNS? DNS provides us name resolution to the IP address for that computer's name. Humans do not understand IP addresses nearly as well as they understand friendly names. So if I'm trying to save a file to my file server 1, I have no idea intuitively what the IP address is for file server 1. But I do know his name is file server 1. So I type in, I want to send this to file server 1. Well, DNS is the service that converts that friendly name that is intuitive to us humans, file server 1, into the IP address for file server 1. So it's a database of these mappings of friendly name to the IP address. And almost all nodes will need at least one and ideally two IP addresses in order to function properly on a larger network. Here we see the family of IPv4 IP address classes. We have a class A, B, C, D, and E. Now, on corporate networks and on the internet, these nodes are all identified by IP addresses out of classes A, B, or C. These ranges, class A is 1 to 126, B is 128 to 191, and class C is 192 to 223 in the first octet of the IP address. These ranges are the ranges of IP addresses that you can assign to nodes on networks. Now, Class D is reserved for a special protocol called Multicast, or Internet Group Management Protocol, IGMP. And in this case, a multicast protocol will send one data stream out from a source computer, and it will assign Class D IP addresses to any number of nodes, client computers, that opt in for this particular transmission. So suppose we have a meeting that I've recorded and I want to send it out to 10,000 clients. I don't want to build a TCP session to every one of these clients because of all the overhead associated with it. So what I'm going to do is I'm going to set up a multicast transmission, and I'm going to identify to these 10,000 clients, we're also going to bind a second Class D IP address to your network interface card, and we're going to pick a number, let's say 226.0.0.19, and I'm going to give that same IP address to all 10,000 recipients that I want to receive this video. And then I'm going to send my video stream out to that same IP address. And the routing system will duplicate and distribute these frames to those 10,000 IP addresses that are all that same number that I identified. So that's the nature of multicast. So therefore, typically it's an application that sends those IP addresses or assigns those IP addresses to nodes. Finally, that Class E IP address is experimental, and generally we can't assign anything out of that either. So the Class D and E aren't IP addresses we generally would assign to nodes, statically or by DHCP, but Class D is generally assigned by application, and Class E is generally not assigned at all. Down below, we see a series of IP address ranges that are defined for private networks and generally are not usable. The first three are not usable on the public internet. So all the routers on the public internet are configured to discard or drop any packets with a source or destination in any of these three ranges, the 10 dot, the 172.16 dot, and the 192.168 dot. These are private address spaces to be used behind corporate firewalls. Automatic private IP addressing is an address that gets automatically generated if your node, your client node, does not have an IP address available. It will make one up out of this range. Again, these are not routable. Now, the first three are routable on private networks. This fourth one, 169.254.0.0, is not routable at all because there isn't a default gateway option with automatic private IP addressing. Therefore, we can't find our way through a router. And finally, the 127 IP address range is defined as diagnostic, and this is where we get our loopback address for testing purposes, 127.0.0.1. That's our loopback address. So these are families of IP addresses that are probably some of the more important ranges you should be aware of. In this lesson, we're looking at ways to identify what your current and local IP configuration is. On a Windows computer, you can type the command at a DOS prompt, ipconfig/all, and that will show you all of the details that are available for this particular network interface and the IP configuration that is associated with that network interface card. Now, on a Linux computer, the command is typically ifconfig-a, and you'll get a similar type of collection of information presented back. So in a Windows world, you get yourself to a command prompt, you type in ipconfig/all, and we can identify the host name of the computer. In this case, it's Momotambo. The domain affiliation is boboville.com. We then, looking down below, we see the Ethernet adapter, local area connection. We see the nature of the network interface card. That's the manufacturer and the model number. Below that, we see something called the physical address. Now, this is also referred to as the MAC address, the Media Access Control address, that is hard-coded onto this network interface card. So the first 6 characters of that MAC address represent the manufacturer, and the last 6 characters of that MAC address are a unique value for this network interface card from that manufacturer, defined by the first 6 characters. You notice these are 12 characters in hexadecimal. It's a 48 binary bit string. We scroll down a little bit and we see the link local IP version 6 address. That's just for future reference. We're going to look at IPv6 in another lesson. We'll move down past that. Then we see the IP version 4 address. And in this case, it's 192.168.222.100. And its subnet mask is 255.255.255.0. That equates to a /24 mask. In addition, we see the default gateway of 192.168.222.254. And finally, down below, like the last 2 or 3 lines, we see the DNS servers, and in this case, 2 are listed, 192.168.222.254, and also a second one at 2.2.2.2. That's as if your first DNS server for name resolution at 222.254, if that server is unavailable for any reasons, then go talk to the other DNS server at this 2.2.2.2. Now that IP address is out on the public internet. First 192.168.222.2.54 comes out of the private IP address space. That would be a DNS server on the corporate network. The second one is a DNS server out on the public internet. Moving forward, we're going to take a look at IP version 6, another layer 3 network layer protocol. Now, because we started running out of IP version 4 addresses, they have started generating and implementing IP version 6 addressing. IPv6 uses 128 binary bits, in contrast to the 32 binary bits used by IP version 4. So IPv6 is a much longer IP address, and therefore we have many more addresses available that will allow us to continue to add servers and other systems onto the public internet. Now, IP version 6, because it's the newer version and it has a great deal more configuration ability because of its greater length, we can add extra services into IP version 6. And one of them is called quality of service, which allows us to prioritize packets. Typically, these would be time-sensitive packets like voice and video. We can say, because this is time-sensitive, let him go to the front of the line and let him zip through the network faster than other lower priority packets. So quality of service is generally for time-sensitive packets on a network, and the infrastructure has to have the ability to recognize QoS, but then if it does, knows how to prioritize these and let them go at the head of the line first. IPv6 also has encryption built into it. That was a weakness that IP version 4 did not. We had to generate a brand new protocol called IPsec, Internet Protocol Security, that is different from IP in that added encryption to the IP packets. Now, back to IP version 6. IPv6 address, as you can see here, in this example, starts with FE80. And then there's a whole series of zeros and et cetera, et cetera. So what we see is using something called hexadecimal characters. Hexadecimal is a numbering system that has 16 different characters. So I can count from 0 to 16 without reusing any of the characters. What we see is each section in an IPv6 address has 4 of these hexadecimal characters, and each character represents 4 binary bits. So I get 16 binary bits per section. That's a very long IP address, and I'd hate to have to type that in more than once. However, what we can do with IPv6 is we can omit this long chunk of consecutive zeros. And we simply omit these zeros, and what we notice is a pair of colons side by side. So in this case, we've left out those 12 zeros, but because we know that this address has to be a fixed length, we look for the double colon and we simply insert an appropriate amount of zeros to make this the proper length. So we can omit the zeros to simplify the writing of an IPv6 address. Further, in each of these sections, we can omit the leading zeros. So as we see, this one section has 007E. Well, if we look down towards the bottom, we see that we can actually even throw away those leading zeros, and that section simply has the 7E. Now, the end user and, of course, the routing system and the nodes all must understand and actually automatically accommodate this by filling in any missing characters with zeros. So again, we can do these two things to shorten the length of the written IPv6 address. However, the processing automatically adds all those binary zeros back in appropriately. So this is your IP version 6 IP addressing. Now, these addresses are broken up into different ranges, similar to the way IPv4 is broken up into certain ranges. And we have a public IP addressing called global unicast addresses that start with a prefix of 2000. We have unique local addresses. This is equivalent to IPv4 private addressing, and they start with FC00. We have something akin to the automatic private IP addressing in IPv4 called link local IP addresses. Now, these are automatically generated by each node at boot up, and they start with a prefix of FE80. Multicast addresses begin with a prefix of FF00. We have unspecified loopback and default route addresses as well. Now, because most computers today run both a TCP IP4 stack and an IPv6 stack simultaneously, there are times where you'll be transmitting an IPv6, but you bump into an IPv4 only network. In this case, we have to bury our IPv6 packet into an IPv4 packet, and that's called tunneling. If I'm transmitting an IPv4 and I bump into an IPv6 only network, then I have to do something called translation, and I translate that IPv4 address into an IPv6 address. So these are some compatibility or interoperability services that are being utilized as we make the transition from IPv4 to IP version 6. We're picking up here in the TCP/IP suite of protocols. On this slide, we're taking a review of the IPv4 address space so that we can look at the difference between public address space and private address space. As you see on the slide, we have classes A, B, and C for IPv4 addressing. These addresses would be assignable to nodes on a corporate network or on the public internet. Any IP network need to place nodes on. Down below in the blue, we see ranges that are private address space. And if you notice, we have a private address space starting with 10 dot that comes out of the class A. We have a private address space 172.16 that comes out of the class B network range. And we have a 192.168 that comes out of the class C network range. So out of the class A range, everything but this 10 dot network range is public because the 10 dot is private. Out of the class B, everything except the 192.168 address range is public because 172.16 is the private address space. And finally, out of the class D, everything except 192.168 address space is public. 192.168 is the private space out of that range. So the private address ranges are usable only behind corporate firewalls on private networks. And everything else is usable on the public internet. The routers on the internet are programmed or configured so that they will discard any private addresses in the source or destination fields. So these addresses are, while they're routable, they are discarded on the public internet because they come out of the private address space. Now, the public address space is allocated by the regional internet registries. So there are 5 different regional internet registries that are responsible for the allocation, the assignment of the public IP addresses. So these 5 regional internet registries will allocate the public address spaces relative to their geographic locations. Moving forward, we're going to look at the next protocol in this TCP/IP suite of protocols. In this case, it's the Address Resolution Protocol, or ARP. Now, this is a Layer 2 data link layer protocol. Frames are the Layer 2 component as we send our data down through the OSI model, through the network stack. A frame is what actually commutes across the media, across the network, from one node to the next node. A frame is generated at layer 2, the data link layer of the OSI model, and it is transmitted from a source MAC address, that's a media access control address, to a destination media access control address. Now, the source address is hard-coded onto the sender's network interface card. As the sender is preparing this frame for transmission, all it does is look up his own MAC address and he populates the source MAC address field. However, the source computer must identify the MAC address of the next hop. That would be the next node we're going to hand this frame to on its path to the actual destination. In many cases, that next node, that next hop, is the default gateway or the router that is the node's connection point to all other subnets and segments. In that case, where the destination is on the other side of a router, the local system, the source system, would send out a ARP request for the MAC address of the default gateway. And then once the router hears that request, the router will say, hey, that's me, and here is the MAC address for my network interface card. Now the sending computer can populate the destination MAC address field and then complete the frame by calculating the cyclic redundancy check, which is sort of a crude hash value for verification of completeness, of integrity, if you will, to make sure that the frame hasn't gotten corrupted in transmission. And at that point, the frame is complete. So before we can complete the frame and send that frame out onto this network medium, we must populate the destination MAC address field, and that's what ARP helps us do. Now, by the time I get to layer 2 of the OSI model here, as I'm processing my data down through the network stack, I've already identified the destination IP address. And this is where a routing decision has to be made. If the destination node is actually on my local subnet, my local IP subnet, I can hand the frame to him directly. And I'll ARP out for his MAC address. And I'll say, hey, the guy with this IP address 192.168.10.15, for example, I need your MAC address. Well, all the nodes will look at their IP address and say, nope, not me, nope, not me. Eventually, the guy who has that IP address will say, oh, that's me. And here, by the way, is my MAC address. So he responds back with an ARP response that says, I'm 192.168.10.15, and here's my MAC address. Boom, that's how the source can populate that destination field MAC address. Now, once the sender receives that ARP response, he'll cache that information in memory for 10 to 15 minutes, depending on the network operating system you're using. And he'll have it memorized now, so he doesn't have to ARP out for it a second time, because typically you're going to send a destination more than one frame. So I'll memorize it and I'll just pull that out of memory, and I'll only go get a fresh cut in 15 minutes if I'm still communicating with that destination. Now, this lends itself to a particular attack, a vulnerability with ARP, and that is if a bad guy can convince your computer that while he's not really 192.168.10.15, for example, he might convince your computer that he is, and he'll send his MAC address to your computer as an ARP response. And now your computer thinks it's actually sending to the legitimate destination of 192.168.10.15. Really, he's sending his information to the bad guy's MAC address. And so this is called ARP cache poisoning. It's a fairly common and dangerous attack. There still is a vulnerability of ARP cache poisoning, even on today's relatively sophisticated and much more secure networks than they ever were before. So we'll probably take a closer look at ARP cache poisoning later when we get looking at the different attacks on networks. Now here we see the actual network captures as we look at frame 5 on the slide. In the left-hand side, we see that this is an ARP request. And it basically says, whoever has 131.107.2.100, tell 131.107.2.216. And then as we look on this capture on the right, the network capture on the right, analyzing frame number 6, we see a response back that says, I am 131.107.2.216, and here is my MAC address. So here we see the ARP request and the ARP response. This completes our lesson on the TCP/IP suite of protocols.